Let's take a look at using Karnaugh maps to simplify the function to get a product of sums simplification or an and of or term simplification. So what we have been focusing on is a sum of products implementation, where we've enclosed adjacent ones of the function in the Karnaugh map using our essential prime implicants and other necessary implicants. And then we identify the simplified min term, which is a product term. The simplified function then is the or the sum of each of these product terms or and terms. And we call that the SOP, or sum of products simplification. For the product of sum simplification, we want to encircle or enclose the adjacent zeros of the function using, again, essential prime implicants and other necessary prime implicants. We want to then identify the max term, which are sum terms. And the simplified function then will be the product or the and of these simplified sum terms, or the and of the or terms. And we refer to that as our product of sum simplification. An alternative method for the product of sum simplification is to solve for the complement of the function, or f prime. So we still enclose adjacent zeros of the function using our essential prime implicants and other necessary prime implicants, but we identify then the simplified min term or product term, which we might be more used to. And then the simplified function is the complement of the function that we're looking for. So what we found is f prime, but it's going to be a sum or of each of these product terms. So what we have to do is a next step, an algebraic step, and solve for the complement of that function, because the complement of the complement, or f prime prime, is equal to f by our involution theorem. So to complement an entire function, we use De Morgan's theorem, and that complement of the sum of products simplification will result in a product of sum simplification. So let's review our max terms before we look at some examples. If we look up here in cell 000, we've been referring to that as min term 0. Well, it's also max term 0. The max term is the sum that will make the cell equal 0. So our max term 0 here, since we have a function of w, x, y, and z, that's w or x or y or z. So then if they're each 0 or 0 or 0 or 0 is the only thing that's going to give us a 0. So whereas if it was a min term, it was w prime and x prime and y prime and z prime. For our max terms, we do not complement when the variable is represented by a 0 in that cell. And again, that's because we're looking for the or term that is represented by a 0. That's our definition of the max term. So if we find adjacent cells, we'll show this algebraically. You don't need to do this, but we'll just prove it algebraically. If we take the and of these two max terms, where we have w or x or y or z, anded with w or x or y or z prime, then by distribution theorem, we can pull out this wx or y, wx or w or x or y, right? Involution, that's distribution and associative theorem. And that becomes anded then with the z or z prime here. And z or z prime, well, that's just equal to a 1 by our identity theorem. So we end up with w or x or y. When we're looking at these two cells, we say, okay, z changed from 0 to a 1, so we won't include it. We just have to remember that w or x or y, there's zeros, so we are not going to prime any of them when we're using our k-maps. So we create the or term of each literal that does not change in adjacent cells. It's unprimed if the literal stays as 0. It's primed if the literal stays as 1. So again, w or x or y is equal to 0. If w is equal to 0, x equals to 0, and y is equal to 0. So let's just take a look at these. This is the same Karnaugh map. And at the left, we've simplified it using sum of products. On the right, we've simplified it using product of sums. So on the left, we've encircled adjacent ones using our essential prime implicants. And on the right, we've encircled the zeros to product of sums, circled the zeros, and created these max terms. So again, the big difference is we've encircled the zeros. So these zeros here, what we have is b state as a 1, and we have D state as a 0. So we're going to do B prime because its state is a 1, and we're going to use D because its state is a 0. And then, in this encirclement here, A and B, they're both a 1, so we use A prime or B prime, these ANDed products. And again, here, C, D don't change, they're both 1s, so we use C prime or D prime. We use the prime of each of these terms. All right, so let's look at how we would implement both of these. Why would we want to solve in the different ways? Well, the sum of products, that's AND gate feeding an OR gate, where the product of sum is an OR gate feeding an AND gate. There is really not a lot of advantage in terms of number of transistors. If we consider the number of transistors in an AND and OR gate the same, we have simplified using product of sums that instead of using a 3-input AND gate, we've just used all 2-input OR gates. They both have to feed 3 terms into the second level gate. There may be another reason that we want to use OR gates, or we'll look at whether we want to use NAND implementation for sum of products and NOR implementation for product of sums. So let's look then at this example where we want to simplify as product of sums, but we're given the function in terms of the sum of minterms. So since we're given it in terms of the sum of minterms, we're going to load 1s where the minterms are. So we have at minterm 1, we're going to load a 1. At minterm 3, we're going to load a 1. At minterm 4, at minterm 5, at minterm 7, and here at minterm 15. So we've loaded the 1s, although we want to simplify in terms of sum of products, so we want to encircle the 0s. We want to simplify in terms of product of sums, so we want to encircle the 0s. We want to start with what are the essential prime implicants. So if we look at this cell here, which is a 0, it can be covered. It can't be covered by this row because the 1's in the way, but it can be covered by the 4 corners. And there's no other way to cover that with 4 cells. So if we were going to use our max products, we'd say that our function, a function of A, B, C, D, we'll write that out. So what we covered there, that's going to be, as a product term, it would be B prime, D prime, but as a sum term, it's B or D. And then we're going to AND that. All right, so that's this here. So we've covered all these cells. So let's look at what we can cover next. That's this one here. Let's, if we look at this one here, well, that can be covered by these 4, and that's the only way for it to be covered by 4 cells. So we'll use that, and let's just circle it. Circle that. And in this one, A doesn't change. A doesn't change, and it's a 1, so we're going to use A prime. And C doesn't change, and it's a 0, so we're going to use C. So we get A prime or C from these 2. So now let's choose another one here. Let's look at, we got to cover these 2, and we've got to cover this 1. So if we look here at this 0, choose this 0 there, it hasn't been covered. We can encircle that with all 4 of these, right? So we can take all 4, and that's going to be where C is a 1 and D is a 0. So we use C prime or D. And that's this one here, right? And then lastly, we just have this 1 cell to cover. So this 1 cell we can cover here, and that's going to be A prime or B. And we'll just do that in blue to make it clear what each of these are. So now let's compare that to using our alternative method where we still are encircling the 0s, and what we want to find is F prime, right? So what we get is f prime, and that's going to be equal to, so the four corners as a product term is b prime d prime. And then this green encirclement, that's going to be a, so we'll OR that with a, a c prime, right? A and c prime. And if we take, I guess the next one we took was the pink. So the pink encirclement, that's going to be C, D prime, and the blue encirclement, that's going to be A, B prime. So that's giving us F prime. That's giving us the complement of the function. So if we want to find the function F, we've got to take the complement of the sum of products of the complement. So then we'll end up with our, when we do that, we can do it in multiple, we'll just do it in one step, but the ORs change to ANDs, and then we complement each literal, right? So we end up with B or D, A prime or C, C prime or D, A prime or this should be B prime. This AB, where's this AB from? This up here should be AB prime. We did that wrong. So that'll be A prime or B. And we get the same result with both of these methods. With this method, we can do it in one step. With this method, we have to take the complement, and we need to then use our De Morgan's theorem to do it in the second step. So in this case, we have solved for F, right? Because F is equal to F prime prime using involution theorem. So both methods we solved for F, and we got our result in terms of the product of sums simplification.